Yes, good morning everyone. In the previous class, we have discussed about the analytic function and CR equations, derivations of the CR equation. Yes, in the CR equations, we written the statement, what is that? Here it is, they are the necessary condition for the function to be analytic. That means, if you take the function f of z is equal to u of x comma y plus I v of x comma y, and yes, u of x comma y, v of x comma y, the partial derivatives are existing, that dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y existing, and yes, if dou u by dou x is equals to dou v by dou y and dou u by dou x, dou y is equals to minus dou v by dou x, then the function is analytic. That means if the function is analytic, the function should follow the conditions, right? If the function satisfying the condition, the function may be analytic, may not be analytic. In the last class I given the example for that one. Now it's a time for discussing the sufficient conditions for a function to be analytic. Here sufficient conditions for a function to be analytic. Okay? If you take any function f of z, when the function becomes analytic, what conditions we are going to verify to show the function is analytic in a certain domain, right? Suppose real and imaginary parts, if you take u of x comma y is equal to, f of x z is equal to u of x comma y plus I v of x comma y, u of x comma y, v of x comma y, this is a real part and this is a imaginary part, and having continuous first order partial derivatives. The functions are continuous there in the CR equations, but the first order partial derivatives are continuous here. U of x comma y, the first order partial derivatives are dou u by dou x, dou u by dou y. For v of x comma y, the partial derivatives are dou v by dou x, dou v by dou y. They are continuous, right? Not only continuous here, and having continuous partial derivatives in the domain D, if you consider the region D, right? If u of x comma y and v of x comma y satisfying CR equations, the first order partial derivatives are continuous in that domain and satisfying the CR equations at all the points in the region D, then the function f of z is analytic. Is it clear for the difference between the necessary condition for the necessary condition for the function to be analytic, and it is a sufficient condition the function to be analytic? In the necessary condition for the function to be analytic, we don't check whether the partial derivatives are continuous or not. But here it compulsory we need to verify if the partial derivatives are of real and imaginary parts are continuous, then we say that the function is analytic in the entire domain D. So in this case, I and f dash of z can be written as ux, that is partial derivative of u with respect to x, plus ivx, that is dou u by dou x plus I dou v by dou y. Or if we go for the CR equations, ux is replaced by vy, the function is satisfying the CR equations, and vx is replaced by minus uy. So dou v by dou y minus I dou u by dou x. This is sufficient condition. I think no need for the proof of sufficient condition for function to be analytic. In the last class we proved the CR equations, right? This is a sufficient condition the function to be analytic, right? Now coming to the example, using CR equation show that the following functions are as first one is analytic at any point, it is not analytic at any point, it is analytic all points except z is equals 0. Now I am going to prove one by one, right? First coming to the first solution, what is the given function here? Given that f of z is equals to mod z whole square, but it is a magnitude of a complex number. If you take z is equals to x plus iy, mod z whole square is nothing but square root of x square plus y square whole square. So we have it is x square plus y square. That implies f of z is equals to u of x comma y, that is x square plus y square plus I into 0. That is let u of x comma y is equals to, which is same as u of x comma y plus I v of x comma y. Here u of x comma y right. Sorry, first question, f of z is equal to mod z whole square is not analytic at any point. Given that f of z is equal to mod z whole square, from this we have the f of z in the form of x square plus y square plus I into 0. Yes, that is it in the form of u of x comma y plus iv of x comma y. Here u of x comma y is equal to what? U of x comma y is equal to x square plus y square, and v of x comma y is equals to 0. Yes, from this I am going to write the partial derivative of u with respect to x. Dou u by dou x is equals to 2x. Dou u by dou y is equals to, yes, y square derivative with respect to y is 2y, and dou v by dou x is equals to 0. Dou v by dou y is equals to 0. Right. From these partial derivatives, clearly, yes, dou u by dou x is 2x, it is continuous. Dou u by dou y is equal to 2y, continuous. Dou v by dou x is equal to 0, dou v by dou y is equal to 0, they are also continuous. And if you are thinking about the sufficient condition for the function to be analytic, the function f of z having continuous partial derivatives, right? And not only having the continuous partial derivatives, and the function is satisfying the CR equations, then the function is analytic in the certain region, certain domain, right? But if you are thinking about the whether the partial derivatives are satisfying the CR equations or not, dou u by dou x is equal to dou v by dou x. It is clear that 2x is not at all 0, 2y is not at all 0. If you are thinking more than 2x is not equal to 0, 2y is not equal to 0. If x is equal to 0, they are going to satisfy, right? If x is equal to 0, yes, if x is equals to 0, that implies dou u by dou x is equals to dou u by, and that means the function may be analytic at 0. Other than 0, that is not analytic. It is clear that whatever x comma y we are taking, the function is not satisfying the CR equation. We don't think about the analytic. But if I am taking x comma y is equal to 0, I have some confidence, right? Yes, that means there is a possibility. Is there? I'm trying to check. Is there any possibility to the function f of z to be analytic at z is equals to 0? In that sense, I'm going to take, if x is equal to 0, dou u by dou x, that is equal to 0, and dou u by dou x is equals to dou v by dou y. Very good. Next, if y is equals to 0, here it is dou u by dou y, that is 0, which is equals to minus dou v by dou x. Okay. At x comma y is equals to 0 comma 0, yes, the function f of z satisfies CR equations, right? CR equations. But since f of z is equals to what we have, f of z is equals to mod z whole square. F of z is equals to mod z whole square. It is not differentiable at z is equal to 0. Last class I given the form of problem, right? F of z is equals to mod z whole square is not differentiable. Not differentiable at z is equal to 0. You may check it whether it is differentiable or not. Limit x tends to 0. That means by the definition, limit z tending to 0, f of z minus f of 0 divided by z minus 0. Yes, if you are writing the limit is not exist, so it is not differentiable. It is not differentiable. Suppose if you take the 0, if you want to go for the analyticity, if this is a 0, z is equal to 0, this is the neighborhood of 0, the function is not differentiable at z is equal to 0. It is not, that means when we can say that the function is analytic at a point, yes, when we say that the function is analytic at z is equal to z naught, it is differentiable at z is equal to z naught, and it is also differentiable at every point in the neighborhood of z is equal to z naught. Yes, at z is equal to 0, function is not differentiable. Not differentiable means the function is not analytic in even z is equal to 0 also. Therefore, yes, the function is not analytic at z is equal to 0. Not analytic at z is equal to 0, and other than 0 if you are taking any point, suppose if I am taking z is equals to 1. Z is equal to 1, if I am taking, the CR equations are not satisfying here, right? It is, you will get dou u by dou x is equals to some 2, right? That means the function is not analytic everywhere. If you are taking other than 0, the function is not analytic. If you are taking 0 also, you will get the function is not analytic. Therefore, f of z is equals to mod z whole square is not analytic at any point. Now coming to the second problem. Is it clear? Okay. Listen, by using the CR equations, if you want to prove the function is to be analytic, Right, first condition, you should find the first order partial derivatives, or first we convert the function f of z in the form of u of x comma y plus I v of x comma y. U of x comma y and v of x comma y, we are writing dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y, right? And they are continuous. The first order partial derivatives are continuous. Then you go for the satisfy whether the first order derivatives are satisfying the CR equations or not. If they are satisfying CR equations, you may think the function is continuous, then followed by differentiability. Right, now coming to the second question solution. Second one is where what we are going to prove, f of z is equals to z bar is not analytic at any point. It is similar to the first question. F of z is equals to what we have, it is z bar, it is conjugate of a complex number, is x minus iy, which is equals to u of x comma y plus I v of x comma y. Here it is u of x comma y is equal to what we have, this is x, v of x comma y is equals to minus y. Dou u by dou x is equals to 1, dou u by dou y is equals to 0, dou v by dou x is equals to minus 1, and dou v by dou y is equals to, dou v by dou x is equals to 0, and dou v by dou y is equals to minus 1. Clearly, dou u by dou x is not equals to dou v by dou y, or dou u by dou y is equals to, one equation is satisfying second equation, but first CR equation not satisfying. Or before verifying the CR equations, what I told, whether here the first order partial derivatives are continuous or not. Clearly they are continuous, constant functions, they are continuous. Even the first order partial derivatives of u comma v are continuous, and CR equations are not satisfying. Finally, what we say that therefore f of z is equals to z bar, which is equals to, what is that, x minus iy, is not analytic at any point. So this is the second solution. Now coming to third one. Coming to third one is what is given, f of z is equals to 1 by z, which is equals to 1 by x plus iy. You take the x minus iy divided by x minus iy, which is equals to x minus iy divided by x square plus y square. So f of z is equals to, I am writing x divided by x square plus y square plus I into minus y divided by x square plus y square. Yeah, this is u of x comma y plus I v of x comma y. So u of x comma y is equals to what we have, x divided by x square plus y square, and v of x comma y is equals to minus y divided by x square plus y square. See the question, what you are going to prove is analytic at all the points except 0. I am going to check the analyticity at z is equal to 0. Before going to that, whether the first order partial derivatives are continuous or not, whether the u comma x comma y satisfying CR equations or not. Okay, now coming to dou u by dou x, dou u by dou y separately. Dou u by dou x, you know that is 1 by u by v formula, x square plus y square whole square into x square plus y square into x derivative is 1 minus x into x square derivative is 2x, y square derivative is 0. So we have, what is that, x square plus y square minus 2x square divided by x square plus y square whole square. Here it is x square minus 2x square, this is y square minus x square divided by x square plus y square whole square. This is dou u by dou x. Next coming to dou u by dou y, 1 by x square plus y square whole square with respect to y. Yes, x square plus y square into, here x derivative is 0 with respect to y, minus x into, with respect to y, x square plus y square derivative is 2y. So finally what I am writing here, minus 2xy divided by x square plus y square whole square. This is dou u by dou x. Next coming to the dou v by dou x, dou v by dou x, which is equals to 1 by x square plus y square, 1 by v square whole square, right, x square plus y square into minus y derivative is 0, minus of minus plus y into, yes, what is the derivative of x square plus y square with respect to x, 2x, which is equals to 2xy divided by x square plus y square whole square. This is dou v by dou x. Next, dou v by dou y. dou v by dou y. Dou v by dou y is equals to, right, 1 by x square plus y square whole square into x square plus y square into the derivative of y with respect to y, the derivative of minus y with respect to y is minus 1 minus y into minus plus y into the derivative of x square plus y square with respect to y, this is 2y. So finally we have 1 by x square plus y square whole square plus minus 1 into x square plus y minus x square minus y square plus 2y square. So finally that implies dou v by dou y is equals to 2y square minus y square is nothing but y square minus x square divided by x square plus y square is the whole square. See, this is dou u by dou x, dou u by dou y, dou v by dou x, dou v by dou y. Clearly, except to 0, that means they are existing, they are continuous also, right? We think about the continuous. Next, whether they are satisfying CR equations or not. CR equations. Yes, if you take the dou u by dou x, that is y square minus x square by x square plus y square whole square, dou u by dou y, which is minus 2xy, dou u by dou y is equals to dou u by dou x is equals to dou v by dou y clearly, and dou u by dou y is negative is there, which is equals to negative, already 2xy is there, negative into negative it is positive, so which is dou u by dou y is equals to r minus dou v by dou x. The function is satisfying the CR equations. If the function is satisfying the CR equation, next what you are going to prove? The function is analytic everywhere except 0. First I am going to think the function is differentiable at z is equal to 0 or not, right? So in that case, since f of z is equals to 1 by z, f of z is equal to 1 by z, is it continuous at z is equal to 0? Or before going to the continuity, f of z is not defined at z is equals to 0. If it is not defined at z is equal to 0, limit is not, that is f of 0 is not defined. To check the continuity, what are the conditions? First, f of a is defined, then limit extends to a, f of z exists, sorry, z tending to f of z is exist. Third condition, limit z tending to a, f of z is equals to f of a. Then we say that the function is continuous. Right, here it is f of z is not defined. Not defined means it is not continuous. If it is not continuous, we don't think about the differentiability. Therefore, f of z is not differentiable at z is equals to 0. If it is not differentiable at z is equals to 0, in the neighborhood also, in this neighborhood, except 0, that may be differentiable. At every point, this is very important. Listen, here this is 0, sorry, this is 0, this is the neighborhood of 0, this is the neighborhood of 0. Yes, in the neighborhood of 0, infinitely many points are there. Except to 0, the function is differentiable. But from the definition of the analytic at a point, if the function is differentiable at every point in the neighborhood, including the point, but it is differentiable at every point in the neighborhood, here it is excluding the 0. So what we say that it is not analytic at z is equals to 0. Other than 0, we have the so many ways. Other than 0, the CR equations are satisfying, the limit is existing, the function is differentiable, in the neighborhood also function is differentiable. Other than 0, therefore other than 0, the function is analytic. Yes, finally we write the statement f of z is equals to 1 by z is analytic everywhere except z is equals to 0, right? This is the problem on this now coming to second example, show that the function sin z, cos z, e to the power of z are analytic in z plane, that is finite z plane, and we find that their derivatives also. Now coming to the first one, let f of z is equals to sin z. So where z is equals to what? X plus iy. So which is equals to f of z is equals to sine z, sine of x plus iy. Yes, we have the standard formula, sine of x plus iy is equals to, generally what we are writing, sin a plus b formula, sin x cos iy plus cos x sin iy. Sin iy. This can be written as cos, if you are expanding cos iy, as e to the power of I of iy, as cos iy is equals to e to the power of I into iy plus e to the power of I into iy minus e to the power of I into iy divided by 2. By using this, by expanding, you will get sin iy is equals to e to the power of I into iy minus e to the power of minus I into iy. By expansion, you will get, this can be written as cos sin x cos hy plus I into cos x sin hy, or you may write it directly also, no problem, sin hy, right. Sin of x plus iy is equals to cos x sin x cos hy plus I into cos x sin hy. So it is in the form of u of x comma y plus I v of x comma y. Clear? Here u of x comma y is equals to sin x cos hy, v of x comma y is equals to cos x sin hy. Dou u by dou x is equal to sin derivative, sin x derivative is cos x keeping y is constant, cos hy is also constant, cos hy, right. Dou u by dou y, partial derivative with respect to y, cos hx derivative is sin hx, cos hy derivative with respect to y is sin hy, sin x sin hy, right. Now dou v by dou x is equals to cos x derivative is minus sin x sin hy, dou v by dou y is equals to cos x keeping x is constant, sin hy derivative is cos hy. See, therefore finally what do you say, dou u by dou x is same as dou v by dou x. Is it clear? And dou u by dou y, dou u by dou y, which is equals to minus dou v by dou x, or minus into minus plus sin x sin hy. The function f of z is satisfying what? CR equations. Not only CR equations, right? Here it is, if you take the u of x comma y, if I am taking u of x comma y, which is equals to sin x cos hy. See, you know that the basic function, the elementary trigonometric function sin x is continuous, cos hy also continuous. The function sin x cos hy is continuous everywhere, right? So that is continuous, the partial that is continuous, dou u by dou x, sorry, this is dou u by dou x, no? Dou u by dou x is cos x, dou u by dou x is equals to cos x cos hy. Yes, cos x is continuous, cos hy is continuous, the product is continuous, this is continuous everywhere. And dou v by dou x also continuous everywhere, sin x sin hy continuous everywhere, cos x cos hy continuous everywhere. Therefore the first order partial derivatives of u comma y, that is the first order partial derivatives of u of x comma y and v of x comma y, they are dou u by dou x, dou v by dou x, dou u by dou v by dou u by dou y, dou v by dou y, they are continuous everywhere. CR equation satisfying, continuous everywhere, and the function f of z is differentiable, right, at any point. Therefore finally what we say, that the sin z is, the function f of z is equal to sin z is analytic in the entire z plane or finite z plane. Let's recall the definition. A function f of z is said to be entire function if it is analytic in the finite complex plane, right. That's why we call as sin z analytic in the z plane, finite z plane is same as this is entire function. Give the example for the entire function, sin z cos z and e to the power of z, and they are the examples of the entire functions. Is it clear? The function is satisfying the CR equations. The first order derivatives of u comma y are continuous, right. So we say that sin z is analytic everywhere in the finite z plane. Similarly you may try for cos z. Next we go for third one, e to the power of z. Yes, f of z is equals to e to the power of z, which is equals to e to the power of x plus iy, where z is equal to x plus iy. e to the power of x into e to the power of iy, e to the power of x into e to the power of iy is what? Cos x plus I sin y. Cos y plus I sin y. E to the power of I theta is equals to cos theta plus I sin theta. So this can be written as f of z is equals to e to the power of x cos y plus I e to the power of x sin y. It is in the form of u of x comma y plus I v of x comma y. If you take u of x comma y is equals to e to the power of x cos y, and v of x comma y is equals to e to the power of x sin y. Real part and imaginary part. Dou u by dou x e to the power of x cos y. Dou u by dou y. Cos y derivative is minus sin y minus e to the power of x sin y. Dou v by dou x e to the power of x sin y. Dou v by dou y e to the power of x sin y derivative is cos y. They are same, no? Dou u by dou x is same as dou v by dou y. Dou u by dou y is same as negative of dou v by dou x. So these two functions are satisfying CR equations. And CR equations, if you consider exponential function is continuous, cos y is continuous, therefore dou u by dou x is continuous, dou v by dou x is continuous, dou u by dou y is continuous, dou v by dou y is continuous, right? The first order, you may write it as statement, a long statement, you need to write it. Yes, since the first order partial derivatives are dou u by dou x, dou v by dou x, dou u by dou y, dou v by dou y are continuous, and the function f of z is equal to e to the power of z is satisfying the CR equations, therefore it is analytic in the z plane, right? This is the analytic. Suppose, what about other trigonometric functions, right? If you take f of z is equals to cot z or secant z. Yes, if you take these two functions where the cot z is not defined, for odd multiples of pi by 2. If you take z is equals to 2n plus 1 into pi by 2, the function is not continuous. Not continuous means not differentiable. The odd multiples of pi by 2, it is not differentiable. And other than 2n plus 1 into pi by 2, the function is analytic. Is it clear for cot z and secant z? Right? Next, if you go for f of z is equals to, remaining is what? Tan z and cosecant z. These functions are not analytic at z is equals to n pi. N belongs to z place, right? Where the function is not defined, it is not continuous. Not continuous means not differentiable. Not differentiable means not analytic, right? Okay, this is about the analytic of the elementary trigonometric functions. You may try for log z. Check the analyticity of log z. See, sorry, here there is a mistake. Tan z, secant z are not defining at odd multiples of pi by 2. They are not differentiable at pi by 2. They are not analytic at odd multiples of pi by 2. The remaining cot z, cosecant z are not analytic at z is equals to n pi. Okay, now coming to the next. Right. Show that f of z is equal to z divided by z plus 1 is analytic at z is equals to infinity, or f of z is equal to z is an analytic at z is equals to, not analytic at z is equals to infinity. Now the definition of the analyticity at z is equals to infinity. As the function f of z is said to be analytic at z is equals to infinity if it is analytic, that is if it is f of 1 by z is analytic at z is equals to 0. So here given that for solution, given that f of z is equals to z divided by z plus 1. Okay. Yes, sir, to check the analyticity at z is equal to infinity, from the definition f of 1 by z is analytic at z is equals to 0, right? Let g of z is equals to f of 1 by z, which is equal, replace z with 1 by z, it is 1 by z divided by, given this example also, plus 1, which is 1 by z divided by 1 plus z by z. So which is equal to 1 divided by 1 plus z. So finally what we have, f of g of z is equal to f of 1 by z is, which is equal to 1 by 1 plus z. Right, see this problem? It is differentiable everywhere. F of z is equal to 1 by 1 plus z is differentiable and it is defined for every z. Right, you may check it. Right, z is equal to, if you are writing x plus iy or simplifying, g of z is equal to 1 by 1 plus z is analytic at z is equal to 0, at z is equals to 0, right? It is analytic at z is equal to 0. So finally what we say, that f of z is equals to z divided by z plus 1 is analytic at z is equals to infinity. Yes, to show the function is analytic z is equals to infinity, f of z is analytic at z is equals to infinity, that is equivalently show f of 1 by z is analytic at z is equals to 0. Now coming to second problem. Yes, f of z is equals to, what is that? Z is there. That implies f of 1 by z is equals to, tell me, 1 by z. Listen, at z is equal to 0 function is not defined. At z is equal to 0 function is not defined. Not defined means not continuous. Not continuous, not differentiable. Not differentiable means not analytic. Therefore, f of 1 by z is equals to 1 by z is not analytic. Not analytic at z is equals to 0. If it is not analytic at z is equal to 0 means f of z is not analytic at z is equals to infinity. Yes, this is about the analytic of a function at z is equals to. Right, next coming to the problem. If f of z is equal to u plus iv is analytic, it is clearly given that is analytic. Analytic means it follows the CR equations. Function is analytic, it follows the CR equations of z is equal to x plus iy, and u plus v is given. U plus v is equal to x plus y into 2 minus 4xy plus x square plus y square. Then we need to find u and v. And that means u is real part of f of z, v is imaginary part of f of z, and also find the analytic function f of z. Is it clear for the problem? Here u plus v is given, the function is analytic, then we have to determine u and v separately, and when we have the u and v, you can write it f of z is equal to u of x comma y plus iv of x comma y. Now coming to solution, this model is very important. Is given that u plus v is equals to x plus y 2 minus 4xy plus x square plus y square. That implies u plus v, simplifying it, x into 2x minus 4x square y plus x cube plus xy square plus 2y minus 4xy square plus x square y plus y cube, or this can be written as u plus v is equals to 2x right, 2x plus 2y minus 4x square y plus x square y minus 3x square y, right, xy square minus 4xy square, that is minus 3xy square plus x cube plus y cube. This is u plus v. From this u plus v, we have to determine u and v separately and f of z by using the function is analytic. Function is analytic means using the CR equations. That is a hint for this problem, right? So now differentiating partially with respect to x and y separately, right? So first differentiating partially with respect to x, what we have, ux plus vx, or divide x of u plus v is equals to derivative of first function plus derivative of the second function. So 2x derivative is 2, 2y derivative is 0, minus 6xy, x square derivative is 2x, keeping 3 pi as constant, 6xy, next minus 3y square plus x cube differentiation is 3x square. This is ux plus uy. Next, differentiating partially with respect to y, uy plus vy is equals to 2x derivative is 0, 2y derivative is 2, next minus 3x square y with respect to y is minus 3x square, as y square derivative is 2y, 2y into minus 3x minus 6xy plus x cube derivative is 0, y cube derivative is 3y square. This is ux plus vx, uy plus vy. Now I am going to apply the CR equations, right? As ux plus vx, as vy is equals to what I am writing here. So using the CR equations, see this can be written as ux plus vx, I don't want to disturb this, 2 minus 6xy minus 3y square plus 3x. Next it is uy, or uy is equal, so you may write it, uy is equal to what I am writing, CR equations, dou u by dou x is equals to dou v by dou y. Yes, dou u by dou x is equals to dou v by dou y. So which is, this can be written as what? It is ux is equals to vy, uy is equals to minus vx. So ux plus vx, uy is equals to what I am writing, minus uy is equals to minus vx, vy is equals to ux, vy is same as ux and uy is same as minus vx, which is equals to 2 minus 3x square minus 6xy plus 3y square. Clear now? Just uy is replaced by minus vx, vy is replaced by ux. Okay, listen. Now I am trying to solve, right? I am trying to add and solve. Adding vx get cancelled, ux 2ux, ux 2ux, right? Add yes, 2 to 4. Listen, minus 3x square plus 3x square minus 3y square plus 3y square get cancelled, minus 6xy minus 6xy minus 12xy. You can common 2 and cancel. So ux is equals to, we have ux is equals to 2 minus 6xy. Say this is equation number 1. Next, subtracting. Subtracting, the signs can be changed, minus plus minus plus plus minus, right? Here ux get cancelled, vx 2vx equals to this one get cancelled. Here it is plus 3x square plus 6xy minus 6xy get cancelled, plus 3x square plus 3x square 6x square is plus 3y square, sorry, minus 3y square minus 3y square minus 6y square. So you can common 2 and cancel it, which is vx is equals to, we have vx is equal to what we have, if you common 2, 3x square minus 3y square. Say this is 2. Is it clear? To determine u and v, we have the separate terms, ux is equals to vx, ux is equals to 2 minus 6xy, vx is equals to 3x square minus 3y square. Right, next continuation. Okay, that means you can write it, ux is equals to 2 minus 6xy, ux is same as vy, no? Right, say this is, now this can be taken as equation number 1. This is 1, this is 3. Next, vx is equals to 3x square minus 3y square. Yes, it is same as vx is equals to minus uy. Say this is 4. Using the CR equations, uy is equals to minus vx or vx is equals to minus uy. Now integrating partially with respect to x. Yes, integrating partially with respect to x for 3 and 4. And we should integrating 3 and 4 partially with respect to x. Partially with respect to x, what is the meaning of? The same meaning for the partial derivative with respect to x, partial integrating with respect to x. When we are integrating partially with respect to x, keeping y as constant, right? So integration of, that is ux is nothing but dou u by dou x dx is equals to integration of here 2 minus 6xy dx. There is a constant, that constant I am going to take pi 1 of y. Yes, partially integrating with respect to y, keeping y as constant, function of y also constant. So in this case directly you can write it, dou u by integration differentiation get cancelled, we have u is equals to what we have, 2x dx, it is 2x minus 6 into x derivative is x square by 2, that is minus 3x square, minus 3x square y plus pi 1 of y. So this is equation number 5. Next, integrating v also, integrating dou v by dou x dx, integrating 3x square minus 3y square dx plus pi 2 of y. That implies, see, 3x square dx with respect to y, integration differentiation get cancelled, v is equals to see 3x square dx, that is 3x cube by 3, this is x cube, minus 3y square derivative is 0, which is equals to plus 3y square, keeping y as constant, minus 3xy square, minus 3xy square plus pi 2 of y. Say this is equation number 6. Okay, here to get the u and v, you should find pi 1y and pi 2y. It is clear. Okay, now as u and v we have here uy. I am trying to find uy. No, uy is equals to, uy stands for what? From that u. From this u, I am going to find uy. Uy, that means differentiating partially with respect to y for u. So which is 2x derivative is 0, minus 3x square y derivative is what? Minus 3x square. Pi 1 of y derivative is what? Pi 1 dash of y. Is it clear my point? Here I am going to differentiating u or differentiating phi partially with respect to y, that is uy. Uy is equal to minus 3x square plus pi 1 dash of y. But uy what we have? Minus uy is equal to 3x square minus 3y square, no? Which is equals to, uy is equal to what? Minus 3x square minus into minus plus 3y square. Using this, combining these two equations, right? First integrating with respect to, derivative partially with respect to y for u, you get uy. And since in the previous uy is equals to minus 3x square plus 3y square. From this, comparing this, minus 3x square is common, that is pi 1 dash of y is equals to what? Pi 1 dash of y is equals to 3y square. Pi 1 dash of y is equals to 3y square. In the same way, differentiating, here vy we have. Now differentiating v partially with respect to y, vy is equals to x cube derivative is 0, minus 3xy square derivative is what? Minus 6xy. Pi 2y derivative is pi 2 dash of y. But vy is equal to what? 2 minus 6xy. 2 minus 6xy. Minus 6xy is common. That implies pi 2 dash of y is equals to 2. The derivatives of pi 1y and pi 2y we have, right? Since pi 1 of y is equals to 3y square, now integrating with respect to y on both sides, that is integration of pi 1 dash of y dy is equals to 3 into integration y square dy plus c1 I am taking, where c1 is the integrating constant. Integration differentiation get cancelled. So finally we have pi 1 of y is equals to, what is that? 3y cube by 3. 3 get cancelled, it is y cube plus c1. Okay. Next, pi 2 dash of y is equals to what we have? 2. Integrating on both sides, pi 2 is equals to, pi 2 of y is equals to what? 2y. Integration, here you can write it integrating in the same way, in the similar fashion. Integrating pi 2 of y dy is equals to 2 into integral dy plus c2. That implies pi 2 of y is equals to, tell me, pi 2 of y is, integration differentiation get cancelled, pi 2 of y is equals to 2y plus c2. That means we have pi 1 of y and pi 2 of y. We can write u comma v, using this pi 1 of y, pi 2 of y in the equation number 5 and 6. Substitute pi 1 of y comma pi 2 of y in equation number 5 and 6. Therefore u of x comma y is equals to 2x minus 3x square y plus y cube plus c1. Next, v of x comma y is equals to x cube minus 3xy square plus pi 2 of y is what? 2y plus c2. That means the problem find u and v. The find u and v is over. Real part is over and imaginary part is over. By using this u and v, we are going to write the analytic function f of z. As if the function is analytic, then I am using the CR equations. If it is not, it is not there in the, if it is not given the problem, the function is analytic or not. So we may not apply the ux is replaced by vy, or we may not replace it. Okay. Now, is it clear? Now, since f of z is equals to, last step, I am going to finish. F of z is equals to u of x comma y plus I v of x comma y. U of x comma y, what we have? 2x minus 3x square y plus y cube plus c1 plus v of x comma y x cube minus 3xy square plus 2y plus c2 I into. Okay, this can be written as 2x 2y is there. So 2 common this, if we common 2, x plus iy, next real parts and imaginary parts. Here it is minus 3x square y plus y cube plus I into x cube minus 3xy square, yeah, plus c1 plus ic2. Right, this can be written as f of z is equals to 2 into x plus iy plus I into, I am going to common I. So what we have? I into x cube minus 3xy square. If I common I, you multiply with I, no? Here you should multiply with I. So plus I into, or 1 by I, actually 1 by I. 1 by I, it is nothing but I divided by I minus I into minus 3x square y plus y cube plus c1 plus c2. Thus this can be written as by expansion, this is z I am writing, or this is x plus iy, or plus I into, as if you take this formula, this can be written as x plus iy whole cube plus c1 plus ic2. Right, finally what I am writing here, x plus iy is equal to z plus I into z cube plus I into z cube plus c1 plus ic2 is c, where c is equals to c1 plus ic2. This is the required analytic function. This is the procedure now. Right, u plus v are given or u minus v is given, whatever it may be, whatever the relation in terms of u and v is given. By using that, we are going to evaluate real part and imaginary part separately. Then by using that, you can write the f of z u of x comma y plus I v of x comma y. This is about the finding the analytic function when the relation between u and v is given. Right, sometimes uv is given, sometimes u minus v is given. Okay, thank you.